the final sunset, the story of the sun's death. Hello, and welcome to Strange Attractor. Today we embark on a journey longer than any human lifetime, longer than the history of all civilizations. We will travel into the distant, unimaginably distant future to witness the final sunset. Not the sunset of a single day, but the sunset of an entire world, an entire system that was once our home. We are going to see how our sun will die. Imagine a warm summer evening. You're standing on the shore of a calm ocean, and the salty air gently touches your face. The sun, enormous and golden, slowly sinks below the horizon, painting the sky in shades of pink, orange, and purple. We witness this ritual every day. It is so familiar that we rarely contemplate its true nature. But what if this sunset is more than just a farewell to the passing day? What if it is a rehearsal, a tiny echo of the grand finale that one day awaits the sun, the earth, and everything we hold dear? Our solar system has existed for a very, very long time, about 4.5 billion years, almost since its very birth. On this small blue planet, the third from its star, life emerged. And for all this time, billions of years, we have lived under the light and warmth of the same faithful, stable star. It gave us energy, measured our days and years, and witnessed the birth of oceans and continents, the evolution of countless species. But nothing in the universe is eternal. Even stars are born, live and die, and our sun is no exception. We now stand on the threshold of a great discovery. In recent decades, astronomers have learned to observe the deaths of distant stars similar to our sun. They have seen planetary nebulae, the final gasps of dying stars. They have watched white dwarfs devour the remains of their planets. Every such observation is a glimpse into our own future, a prediction of what awaits our home system. Astrophysicist Melinda Suarez-Furtado once said, "Whether Earth will survive is an open question." And in these words lies all the drama and uncertainty of our future. We are journeying into that future right now. Our ship is imagination. Our fuel is the scientific knowledge gathered piece by piece over centuries of observing the stars. Modern astrophysics allows us to peer into the future with astonishing accuracy. We know our sun's mass, its age, and the speed of the thermonuclear reactions in its core. We can calculate how much hydrogen fuel it has left, how long it will burn, and what will happen when that fuel runs out. These calculations are not speculation. They are precise science, based on the fundamental laws of physics. But between the cold numbers and a living picture of the future lies a vast chasm, and it is into this chasm that we will now leap. Our journey does not begin tomorrow or in 100 years. We are jumping forward 1 billion years. The first signs of the approaching catastrophe. 1,100,000,000 years have passed since the time we call our own. Earth has changed beyond recognition. We are standing on the same shore, but the scene before us is entirely different. The sun in the sky seems larger, brighter. Its light is no longer gentle, but ruthless and scorching. This is not the friendly star we once knew. It has become only 10% brighter than before, but this small change was enough to trigger an irreversible chain reaction. The air is heavy, humid, and unbearably hot. The average temperature on the planet's surface has reached 47 degrees Celsius. The oceans, once the cradle of life, have now turned into giant boiling cauldrons. Look at the water at your feet. It is bubbling, sending thick plumes of steam into the sky. The horizon shimmers in the superheated haze. The sky is no longer blue. It is covered by a dense whitish veil of water vapor clouds, which like a blanket traps the planet's heat, preventing it from cooling. This phenomenon is known as the moist greenhouse effect. For billions of years, the sun has slowly but relentlessly increased its power. In its core, hydrogen continues to fuse into helium, and this process makes the star hotter and brighter. Every second, 600 million tons of hydrogen are consumed in our star's core. But as the hydrogen supply in the very centre of the core dwindles, the reaction becomes even more intense, trying to compensate for the decreasing fuel density. And now, the tipping point has been reached. The last drops of liquid water are evaporating from the surface, rushing into the scorching atmosphere where light, feathery clouds once floated. This process is uneven. First the tropical seas disappear, then the temperate oceans, and finally the last lakes in the polar regions turn to vapour. Rising higher and higher, the water molecules reach the upper layers of the atmosphere. There they are met by harsh solar radiation. It mercilessly tears them apart into oxygen and hydrogen. This process is called photodissociation. Oxygen, being heavier, remains in the atmosphere, gradually accumulating and oxidizing everything around it. The planet's surface becomes covered in rust, metal oxides. Even the rocks take on a reddish hue, similar to the surface of Mars, and the light hydrogen, the lightest element in the universe, leaves the planet forever, escaping into the void of space. This is a slow but certain farewell. Earth is losing its water, its lifeblood, its very essence. Every second, billions of tons of hydrogen are carried away by the solar wind, and this process can no longer be stopped. The planet is drying out, turning into a hot, waterless wasteland. Remarkably, we can observe this process right now on other planets. Venus, our closest neighbour, has already gone through a similar catastrophe. Billions of years ago, it too may have had oceans. But its proximity to the Sun triggered the same greenhouse effect that is now afflicting the future Earth. Today, Venus is a scorched desert, with a surface temperature of 460 degrees Celsius and an atmospheric pressure 90 times greater than Earth's. But even in this hell, life clings desperately to existence. Not on the surface, of course. Nothing can survive here anymore. The air temperature exceeds 50 degrees even at night and reaches 70 during the day. Any complex organic molecules, the basis of life, are destroyed by the heat and intense ultraviolet radiation. But deep underground, in the cracks of rock formations, near geothermal vents where the last liquid water still seeps out under immense pressure, colonies of microbes may still be alive. These are archaea and thermophilic organisms, descendants of the life forms that originated near underwater volcanic vents billions of years ago. They do not see the scorching sun, nor do they feel the boiling atmosphere. They live in their own small dark world several kilometres beneath the surface, unaware that their home has become the antechamber to hell. These microscopic creatures feed on chemical energy derived from the interaction of hot water with minerals. They exist independently of sunlight, just like their ancestors 4 billion years ago. They are the last heirs of the vibrant life that once covered the entire planet. They are the last islands of life in a dying world. Their fate is also sealed. As the planet continues to heat up, the heat penetrates deeper and deeper into the Earth's crust. One by one, the underground water reservoirs evaporate. Even at a depth of 10 kilometres, the temperature gradually rises to a critical point. These last life forms do not have much time left, only a few 100 million years, and yet their resilience is astonishing. Some of these organisms can survive at temperatures exceeding 120 degrees Celsius. They adapt, mutate, and fight for every day of their existence. Perhaps among them are some that will hold on longer than others, becoming the last witnesses of Earth's biosphere. Above them, on the surface, another drama unfolds. The continents, deprived of oceans, begin to crack from the heat. Enormous canyons cut through the land where rivers once flowed. Former seabeds turn into salt deserts, strewn with crystals of salt and other minerals left behind after the water evaporated. The atmosphere grows ever denser with water vapour. The greenhouse effect intensifies exponentially. The more water evaporates, the hotter it gets, and the faster the remaining water evaporates. It is a vicious cycle that can no longer be broken. Earth is entering a phase of a runaway greenhouse effect, from which there is no return. Sometimes, in different parts of the planet, strange phenomena occur. Due to the uneven heating of the atmosphere, monstrous hurricanes form, racing across the continents at speeds of 300 kilometers per hour. These superheated steam tornadoes carry salt and dust for thousands of kilometers, turning the last relatively cool areas into equally scorched wastelands. And at night, when the sun disappears below the horizon, the temperature drops by only a few degrees. The dense atmosphere traps heat like a greenhouse. The stars are not visible through the thick layer of water vapour. The sky glows with a dim orange light, a reflection of the planet's incandescent surface. This is only the beginning. Earth is just starting down the path that will lead it to complete transformation. Ahead lie billions more years of slow agony, during which the planet will lose the last vestiges of its former self. The Age of Deserts. Another 500 million years pass. We look at Earth again, and it has changed once more. The oceans are gone, completely. The last seas evaporated 200 million years ago. In their place are gigantic salt plains, cracked by the heat and covered with bizarre crystals. These crystals are all that remain of the once vast expanses of water. Salt, gypsum, and other minerals form fantastical sculptures that stretch to the horizon. The planet has turned into one continuous endless desert, scorched and lifeless. Dunes of reddish dust extend to the very horizon. This dust is not just sand. It is the remnants of rocks, ground down by time and wind, saturated with iron oxides. The entire planet is covered in rust, having acquired a colour similar to that of Mars. The sky has a strange yellowish-brown hue. It is no longer moist, but dry and dusty. Water vapour has almost completely disappeared from the atmosphere. Its last traces have either decomposed into hydrogen and oxygen or been carried off into space. The atmosphere now consists mainly of nitrogen and carbon dioxide, with small amounts of argon and other inert gases. The sun in this sky is a blinding white disk, painful to look at. Its brightness continues to increase. Over the past 500 million years, it has become another 5% brighter. The surface temperature now ranges from 80 degrees Celsius at night to 120 degrees during the day. These are temperatures at which tin melts and alcohol boils. Earth has become a twin of Venus, its unfortunate sister. The planet is trapped in what scientists call a super greenhouse effect. Carbon dioxide released by volcanic eruptions is no longer absorbed by the oceans as it once was. Instead, it accumulates in the atmosphere, creating a powerful greenhouse effect. For a long time, tectonic activity, the movement of continental plates, continued to operate. Magma from the planet's interior rose to the surface through volcanoes and fissures, releasing vast amounts of carbon dioxide and sulfur compounds into the atmosphere. These gases made the already suffocating atmosphere even denser and hotter. But now even tectonics is beginning to slow down. This complex geological dance required water. It served as a lubricant for the movement of continental plates, allowing rocks to soften and slide against each other. The oceans acted as giant thermoregulators, cooling some parts of the crust and heating others, creating convection currents in the mantle. Without oceans, this system begins to fail. The continental plates move more and more slowly. The boundaries between them become increasingly rigid. Earthquakes occur less frequently, but when they do, they are catastrophically powerful. Volcanic activity is also on the decline. The Earth's crust is gradually solidifying, turning into a single immobile shell. This process will take several 100 million more years, but its direction is already clear. The planet is slowly dying geologically. Its internal heat is still great, but the mechanisms for its release to the surface are broken. The planet's heart continues to beat, but ever more weakly. The landscape of this new Earth is striking in its stark beauty. Where tropical forests once rustled, bizarre stone pillars now rise, carved out of sandstone by the wind. former seabeds have turned into endless plains of white and pink salt, glittering like snow in the bright sunlight. In some places, ancient rock formations are exposed, which for billions of years were hidden beneath thick layers of ocean sediment. These outcrops tell the story of the planet like pages in a stone book. Here one can see traces of ancient impact craters, fossilized remains of reefs, and imprints of long-extinct sea creatures. The wind is the only active force shaping the terrain. It blows constantly, carrying dust and sand, carving amazing shapes into the rocks. Sometimes these winds reach hurricane force, lifting tons of dust into the air and creating sandstorms that can last for months. But even in this lifeless world, amazing things happen. Minerals, deprived of the protective cover of atmosphere and water, interact directly with solar radiation. Some of them change colour under the influence of ultraviolet light. Others form new crystalline structures. The planet's surface is slowly turning into a giant chemical laboratory. And yet, somewhere, deep beneath the many-kilometre-thick layer of scorching rock, in the last isolated reservoirs where water can still exist under enormous pressure and at temperatures above 150 degrees, those same microbes may still be alive, the last of the Earthlings. They have adapted to incredible conditions. Some have learned to extract energy from the radioactive decay of uranium and other elements in the rocks. Others live off chemical reactions between different minerals. Still others have entered a state similar to suspended animation, slowing all life processes to a minimum, waiting for better times that will never come. These microscopic creatures are living fossils, the last witnesses of an era when their world was blue and full of life. Their DNA holds the information of billions of years of evolution, of all the life forms that once flourished on the planet's surface. But there is no one left to read this information. Their time too is running out. The planet continues to heat up from within and without. Their last refugees are slowly boiling away. It is a long agony, stretching over hundreds of millions of years, silent and invisible from the surface. Each generation of these microbes lives in conditions slightly harsher than the last. Each generation is forced to adapt to ever higher temperatures and pressures. Some colonies die out, unable to withstand the next temperature increase. Others migrate even deeper to where conditions remain tolerable. But the planet's depths are not infinite. Sooner or later they will have nowhere left to retreat, and then there will be nothing living left on Earth. Above their heads, on the surface, the slow erosion continues. Wind and sand wear down the ancient mountains. The once majestic Himalayas and Alps have been worn down into low hills. The Andes and the Rockies have been levelled with the plains. The only elevations left on the planet are the ancient shields, the oldest and most durable parts of the Earth's crust that have survived billions of years of geological cataclysms. Time on this dead planet flows in a peculiar way. Days and nights follow each other with the same regularity as they did billions of years ago, but there is no difference between them. During the day, the surface heats up to 120 degrees. At night, it cools to 80. The seasons still exist, but the differences between them are minimal. Summer is only a few degrees warmer than winter. The moon still orbits the Earth, but its influence has become almost negligible. Without oceans, there are no tides. The moonlight faintly illuminates the lifeless deserts, creating a bizarre play of shadows among the salt crystals and wind-carved stone statues. Sometimes meteors can be seen in the sky, remains of comets and asteroids that burn up in the planet's dense atmosphere. But even these celestial visitors cannot break the monotony of the dead world. They flare up and fade away, leaving no trace in the planet's history. The Runaway greenhouse collapse. We jump even further into the future, to the 2 billion year mark from our time. The sun has become noticeably brighter. Now, there is no doubt about what will happen next. Life on Earth, even in its most primitive and resilient forms, is approaching its final end. The temperature on the planet's surface now exceeds the boiling point of water, even at the poles. The average global temperature has reached 150 degrees Celsius. This is no longer a planet in the usual sense of the word, but a giant open-air furnace. The atmospheric pressure has increased several times compared to its original state. The dense atmosphere of carbon dioxide, nitrogen and water vapour creates a monstrous greenhouse effect. Any organic molecules, the basis of life as we know it, were long ago destroyed by the temperature and harsh ultraviolet radiation. The last microbes in their underground shelters finally perished about 500 million years ago, when their aquatic oases evaporated under the onslaught of heat, penetrating deep into the planet. The temperature 5 kilometers below the surface now exceeds 200 degrees. Even the most heat-resistant known organisms could not survive in such conditions. Earth has become completely sterile. Not a single living cell remains, not a single molecule of DNA or RNA. Billions of years of evolution, countless life forms, the entire history of the biosphere, all of it has vanished without a trace, as if it never existed. An eternal, motionless heat reigns on the surface. The winds have become weaker. The dense atmosphere impedes the formation of powerful air currents. But new, strange phenomena have appeared. Sometimes, huge convection cells form in the atmosphere, giant vortices of hot gas that rise from the surface to a height of hundreds of kilometers. The planet's surface has begun to change fundamentally. At temperatures above 150 degrees, many rocks become plastic. Granite softens like modelling clay. Basalt flows like thick honey. Mountains slowly slump, losing their sharp outlines and turning into gentle hills. Once majestic canyons are filled with molten rock. Valleys are smoothed out. The entire planet is slowly turning into one giant plain, covered by a sea of liquid lava. This process is very slow. The changes occur over millions of years, but they are irreversible. The most easily melted minerals, lead, tin, zinc, long ago turned into liquid and flowed into the lowlands, forming metallic lakes. More refractory rocks hold out longer, but their time is running out. At 200 degrees, aluminum begins to melt. At 300, silver. The chemical composition of the atmosphere is also undergoing changes. Many minerals on the surface begin to decompose, releasing various gases. Vapours of sulfur, phosphorus, and various metals enter the air. The atmosphere acquires a caustic, suffocating smell and a yellowish colour. Sometimes strange chemical reactions occur. Vapours of different metals rising into the atmosphere interact with each other and with other gases. Bizarre compounds are formed, which fall to the surface as a multicoloured rain. Iron colours some areas red, copper green, chromium purple. But this is not the rain we know. These are drops of molten metal that fall from the sky at a temperature of several hundred degrees. They hiss as they touch the already scorching surface and instantly solidify, creating fantastic patterns on the rocks. The sun in this poisonous sky looks like a giant white disk surrounded by rainbow halos. These halos are created by the refraction of light in the vapours of various metals and chemical compounds. Sometimes the sky shimmers with all the colours of the rainbow, but this beauty is deceptive. Behind it lies a deadly chemical environment. Day and night hardly differ in temperature. The dense atmosphere traps heat so effectively that the difference between day and night temperatures is only a few degrees. The planet has turned into a giant greenhouse where the temperature is constantly maintained high enough to melt lead. It is strange to think that forests once rustled here, waves lapped, birds sang, that civilizations were born and died here, cities were built, poems were written, and music was composed. Now, not a trace of all this remains. Even the mountains, which seemed eternal, are slowly slumping under the unbearable heat. The geological processes that shaped the planet for billions of years have almost completely stopped. Plate tectonics has come to a final halt. Volcanic activity has ceased. Erosion has also nearly ended. At such high temperatures, rocks become too soft for the wind to break them down. Instead, they simply flow, like a very viscous liquid. Earth is silent. It is an absolute, all-consuming silence of a dead planet. There are no sounds of wind, no thunder, no cracking of cooling stones. There is only the quiet hissing of chemical reactions and the barely audible hum of convection currents in the atmosphere. The planet awaits its end, which is now not far off. The main drama is unfolding not here, but at the centre of the system, in the heart of the aging star. The sun is preparing for its final, most spectacular act. In its core, the inevitable is happening. The hydrogen fuel that has sustained it for billions of years is running out. The agony before the transformation. We take another leap in time to the 4 billion year mark from our era. Now we shift our gaze from the dead Earth to the sun itself. Our star is preparing for its final, most dramatic act. In its core, the inevitable is happening. The reserves of hydrogen fuel that have fed it for over 8 billion years are finally coming to an end. Over the past 2 billion years, the sun has become another 30% brighter. Earth has long since turned into a molten ball, with a surface temperature exceeding 400 degrees Celsius. The continents have dissolved into a sea of liquid lava. The atmosphere has become so dense and hot that nuclear reactions between light elements have begun to occur within it. But this is merely a prelude to the main performance. In the sun's core, the hydrogen is almost gone. The few atoms that remain are so scattered that thermonuclear reactions are becoming increasingly rare. The energy that has kept the star in equilibrium for billions of years is running out. This does not mean the star will simply go out like a candle. The universe is far more inventive. When thermonuclear fusion in the core ceases, the delicate balance between gravity, which seeks to compress the star, and radiation pressure, which keeps it inflated, is broken. Gravity takes over. The star's core begins to collapse under its own colossal weight. This process releases a huge amount of gravitational energy, which is converted into heat. The temperature at the centre of the star skyrockets. Where it was once 15 million degrees, it now climbs to 100 million degrees. This monstrous temperature ignites the hydrogen in the layers surrounding the depleted core. A new phase of fusion begins, not in the centre of the star, but in a shell around the contracting core. This shell fusion is much more intense than before. It releases tens of times more energy. The outer layers of the sun cannot withstand this onslaught. They begin to expand like a balloon. The surface of the star moves further and further away from its centre. The sun enters a stage that astronomers call a subgiant. This is a transitional phase before it becomes a red giant. But even before our star reaches its maximum size, the agony begins. The sun loses its stability. The thermonuclear fusion in the shell occurs unevenly, in bursts. Sometimes the reaction subsides, and gravity compresses the shell even more. The temperature rises, the reaction flares up with renewed force, and the shell expands. Then the cycle repeats. These pulsations affect the entire star. The sun contracts and expands, brightens and dims. Powerful streams of plasma begin to erupt from its surface. This is the solar wind, but now it has turned into a veritable hurricane of superheated gas, racing at speeds of thousands of kilometers per second. This plasma hurricane strikes the planets of the solar system with unprecedented force. Mercury, closest to the sun, is the first to take the hit. Its thin atmosphere is instantly blown away into space. The planet's surface begins to evaporate under the assault of the hot plasma. Venus also suffers. Its dense carbon dioxide atmosphere, which protected the planet from cosmic radiation for billions of years, begins to break down. The upper layers of the atmosphere are stripped away and carried off by the solar wind. Earth, long deprived of life, meets this blow head-on. But even its once powerful magnetic field cannot withstand such an assault. The planet's magnetosphere, which protected it from cosmic radiation for billions of years, begins to crack and tear under the pressure of the plasma flows. First, the outer radiation belts, rings of charged particles that surrounded the planet, disappear. Then the main magnetosphere collapses. The solar wind gains direct access to Earth's atmosphere, And then begins the process that astronomers call atmospheric erosion. The powerful stream of charged particles from the Sun literally strips the planet of its gaseous envelope. Molecule by molecule, atom by atom, Earth's atmosphere is carried away into interplanetary space. This process is uneven. First, the lightest gases, hydrogen and helium, disappear. Then comes the turn of water vapour, carbon dioxide and nitrogen. The planet's dense, once suffocating atmosphere gradually thins out. The greenhouse effect weakens. The surface temperature begins to fall. But this is not a return to life. It is the agony of a dying world. As the atmosphere thins, the planet's surface is increasingly exposed to solar radiation. Harsh ultraviolet and X-rays penetrate deeper, destroying even the most resilient chemical compounds. The process of atmospheric loss stretches over hundreds of millions of years. It is not an instantaneous catastrophe, but a slow death. Every day, Earth loses billions of tons of gas. Every month, the atmosphere becomes a little thinner. Every year, the planet increasingly resembles an airless desert. By the end of this period, only traces of Earth's once dense atmosphere remain. The atmospheric pressure drops 1,000-fold. The surface of the planet is now in a near-perfect vacuum. During the day, the temperature rises to 300 degrees under the rays of the unstable sun. At night, it drops to minus 150 degrees. Earth has become a dead, airless ball, similar to the Moon or Mercury. Its surface is covered with solidified lava, formed during the era of the most intense greenhouse effect. In this lava, as if in amber, the final chapter of the planet's history is eternally preserved. The sky above this dead world is black, dotted with unwavering stars. The sun in this sky looks much larger than before. It is no longer golden, but white, almost silvery. Its light is harsh, cold, despite the high temperature. It is the light of a dying star. But this is only a prelude. The main performance is yet to come. The sun continues its transformation, preparing for the final act of the cosmic drama, which the entire solar system will witness. The birth of a monster. 7 billion years in the future. The sun has completed its transformation into a red giant. Look at the sky from the surface of the airless Earth. It is black, dotted with bright, unblinking stars. But almost half of this sky is occupied by it. An enormous crimson-orange sphere that is hard to call the sun in the familiar sense of the word. It is a monster, terrifying and beautiful in its grandeur. Our star's radius has increased 256 times. Whereas it could once fit 1.3 million Earths, it can now fit nearly 20 billion. Its luminosity has increased 2,700 times. Paradoxically, the star's surface temperature has dropped from 6,000 to 3,500 degrees. The sun has become cooler, which is why its colour has changed from yellow to red. But its gigantic size more than compensates for the low temperature. If our star were in the position of the current sun, its surface would have engulfed the orbits of Mercury and Venus. Earth's orbit would pass within the star, in its rarefied outer layers. But over billions of years of evolution, the planet's orbits have changed. As it transformed into a red giant, the sun lost a significant portion of its mass. A powerful stellar wind carried nearly a third of the solar material into space. And according to the laws of celestial mechanics, if the central body loses mass, the orbits of the planets revolving around it expand. Earth has moved further away from its parent, but not far enough. The planet's surface is now an ocean of molten lava. The temperature here reaches 1,500 degrees Celsius, hotter than the melting point of iron. The rocks, the continents, everything that once constituted the planet's solid crust has turned into a boiling red magma. The planet glows with its own dim light, like a giant ember. But Earth is not the only one to suffer from the sun's transformation. Mars, once a cold and dry planet, is now experiencing an unexpected revival. The temperature on its surface has risen to a comfortable 20 degrees Celsius. The polar ice caps have melted, releasing vast amounts of water vapor and carbon dioxide. The planet has developed a dense atmosphere, and temporary lakes and seas may have even formed in the lowlands. For a few 100 million years, Mars has become the most hospitable place in the inner solar system. If any dormant life forms, such as spores or cysts, had survived in deep underground layers, they would have a chance to be revived. But this is a temporary respite. The red giant is unstable, and its brightness continues to grow. And what about the outer planets? Jupiter, Saturn, Uranus and Neptune are at a safe distance from the bloated star, but even they feel its influence. The temperature in their atmospheres has risen by hundreds of degrees. The icy moons of these giants, Europa, Ganymede, Enceladus, Titan, have begun to melt. Europa, covered by a thick shell of ice, has turned into a water world. Its icy crust has melted, revealing a deep ocean of liquid water. Perhaps primitive life even emerged in this ocean, taking advantage of the unexpectedly favourable conditions. Titan, Saturn's largest moon, has also changed dramatically. Its dense atmosphere of nitrogen and methane has heated up so much that its methane lakes and seas have turned to vapour. The surface, hidden under a thick layer of organic compounds, has become visible for the first time in billions of years. Even distant Pluto has felt the breath of the dying star. Its nitrogen atmosphere, which usually froze and fell to the surface as snow, now remains gaseous even in winter. The water ice beneath the dwarf planet's surface has begun to thaw, possibly forming a subsurface ocean. But all these changes are mere side effects of the main drama. At the centre of the system, events of a much larger and more destructive scale are taking place. The red giant is extremely unstable. The thermonuclear fusion processes in its core are erratic, occurring in bursts. The star pulsates, expanding and contracting. With each pulsation, enormous masses of stellar material are ejected into space. These ejections travel at speeds of hundreds of kilometers per second, sweeping away everything in their path. Comets and asteroids caught in these streams evaporate instantly. Interplanetary space becomes filled with hot gas and dust. The solar system turns into one giant nebula, at the centre of which a dying star pulsates. Visibility between the planets drops to zero. Space becomes opaque with dust and gas. And here, future astronomers face the main mystery, the key question for which there is still no definitive answer. What will be the ultimate fate of Earth? Will the planet survive the red giant phase, or will it be swallowed by the expanding star? There are two main scenarios, and scientists debate which is more likely. The first, more optimistic scenario is based on the Sun losing mass. During its transformation into a red giant and subsequent evolution, the star could lose up to 40% of its material. According to the laws of celestial mechanics, this would cause the orbits of all planets to expand. Earth would move further away and could avoid being engulfed, though it would become a molten, lifeless ball. The second scenario is grimmer. The bloated outer layers of the red giant create drag on the planet's motion. Earth, orbiting, would literally break against this rarefied but still tangible stellar atmosphere. Furthermore, the tidal forces between the giant star and the small planet would act with monstrous power, gradually pulling Earth towards the Sun. Which scenario is correct? Most modern calculations, taking into account all factors, the star's mass loss, tidal breaking, drag from the stellar atmosphere, lean towards the second option. Earth's fate is most likely sealed. It will be consumed by its parent. But even if the first scenario proves true and Earth survives, its future will not be bright. The planet will forever remain a dead, molten ball, orbiting the gradually cooling remnant of the Sun. Its surface will never again have water, an atmosphere, or life in any form. Meanwhile, the red giant continues its evolution. In its core, the helium reserves are running out. The very helium that was formed from the fusion of hydrogen over the previous billions of years. Now, carbon, the product of helium fusion, is put to use. But carbon burns even less stably, even more explosively. The star is entering the final stage of its evolution. It is becoming increasingly unstable, increasingly unpredictable. Its brightness can change by a factor of 10 in just a few days. Powerful ejections of material follow one after another. The sun is preparing for its last act, shedding its outer layers and transforming into a white dwarf. The Planet Eater. 7,600,000,000 years from our time. The end is near. The sun, having reached the peak of its giant phase, begins to devour its own creations. The process is as inexorable and majestic as the ticking of a cosmic clock. First in line is Mercury. The closest planet to the star was doomed from the beginning. It has no chance of survival. Millions of years before its final engulfment, Mercury's atmosphere completely evaporated under the stellar wind's assault. The planet's surface heated to 2,000 degrees and began to slowly vaporize. But the real drama begins when the expanding outer layers of the sun reach the planet's orbit. Mercury plunges into the boiling photosphere of the star and literally dissolves within hours. The planet's iron core, its silicate mantle, all the matter that constituted it for billions of years, mixes with the star's substance and vanishes without a trace. An observer from a safe distance would see no dramatic explosion. The planet would simply become a dimmer and dimmer point of light until it disappears completely. It is a quiet, almost imperceptible death of a world that existed for 4.5 billion years. Next in line is Venus. Its fate is sealed. The planet that might have once resembled Earth but turned into a hell due to the greenhouse effect now meets its final end. Its dense carbon dioxide atmosphere, its surface heated to 400 degrees, all of it dissolves into the substance of the star that the planet was once a part of billions of years ago. Venus lasted a little longer than Mercury due to its wider orbit, but the outcome was predetermined. Tidal forces tore it apart even before final contact with the sun's photosphere. The planet stretched into a giant drop of molten matter, which slowly dissolved into the star's substance like a sugar cube in hot tea. And then comes Earth's turn. Slowly, orbit by orbit, our home planet approaches the fiery wall of the red giant. This process takes thousands of years. First, Earth enters the rarefied outer layers of the stellar atmosphere. Friction against this atmosphere slows the planet down, causing it to spiral slowly towards the star's center. Tidal forces of unimaginable power begin to tear the planet apart. The solid crust cracks and breaks. The molten mantle is squeezed out in enormous fountains of lava. The planet's iron core deforms, taking the shape of a giant egg elongated towards the star. The surface temperature reaches 3,000 degrees. Rock flows like water. Metals vaporize and rise into the atmosphere as bright clouds of steam. The planet glows with its own light, like a small star, and then it touches the dense layers of the sun's photosphere. There is no explosion, no loud finale. Earth simply, quietly, and inexorably dissolves into the substance of its parent. The iron of its core, the silicon and aluminum of its mantle, the oxygen of its former oceans, all of it becomes part of the sun. Over a few tens of thousands of years, the planet that existed for 4.5 billion years ceases to exist. The only thing that remains of Earth are faint spectral lines of metals in the star's atmosphere, lines of iron, magnesium, silicon, the chemical signatures of a world that was once home to billions of life forms. Future astronomers, studying the spectrum of the cooling white dwarf, will be able to detect these lines and understand that planets once existed here. But the drama does not end there. Mars, the fourth planet from the Sun, is also doomed. Although its orbit expanded due to the star's mass loss, it was not enough. The red giant continues to grow, and eventually swallows it too. Even the giants of the outer solar system feel the breath of the dying star. Jupiter, Saturn, Uranus, and Neptune, being at a relatively safe distance, survive, but their satellite systems are ravaged. The icy moons melt and evaporate under the intense radiation. Europa, which for billions of years harboured a deep ocean beneath its icy shell, now becomes a water world with a dense atmosphere of water vapour. Enceladus, a small moon of Saturn, is also freed from its icy shell. Titan loses its methane seas. They evaporate into the thinning atmosphere. The famous rings of Saturn, composed of billions of ice particles, disappear within a few thousand years. The ice evaporates, and the dust is scattered by the solar wind. Saturn becomes an ordinary gas giant stripped of its main adornment. The asteroid belt between Mars and Jupiter also ceases to exist. The small rocky fragments vaporize almost instantly. Even large asteroids like Ceres and Vesta cannot withstand the heat and intense radiation of the red giant. Surprisingly, some distant objects in the solar system get a new lease on life. Pluto and other dwarf planets in the Kuiper belt find themselves in a zone where the temperature becomes comfortable for liquid water to exist. Their frozen surfaces melt, forming temporary atmospheres and perhaps even oceans. For a brief period, just a few 100 million years, these distant worlds may become the last oases of warmth in the solar system, but their time is also limited. The red giant is unstable and continues to evolve towards its final transformation. We are not just fantasizing about a distant future. Very recently, astronomers obtained direct evidence of such processes. In 2023, they observed for the first time a star similar to our Sun engulfing a Jupiter-sized planet. The process took about 100 days, and the flare was visible from a distance of 12,000 light-years. This observation confirmed theoretical predictions and showed that the engulfment of planets by red giants is not a rarity in the universe. A similar fate, it seems, awaits billions of planetary systems throughout the galaxy. The Last Haven, an unexpected renaissance on the outskirts. But while the inner planets perish in the fire of the expanding star, something wonderful and beautiful is happening on the system's farthest outskirts. There, where eternal impenetrable darkness and a cold close to absolute zero have always reigned, an unexpected cosmic spring begins. Look at Pluto. This tiny, once-forgotten dwarf planet is transformed as if by magic. The rays of the distant but powerful red giant carry enough heat to melt its perpetually frozen surface. The nitrogen and methane ice that covered the planet in a thick shell begins to melt and transforms into a dense atmosphere. The temperature on Pluto's surface rises from minus 230 degrees to a comfortable minus 10, and in some areas, even to positive values. Beneath the melting ice crust, a dark surface rich in organic compounds is revealed. Perhaps, in the depths, beneath kilometres of ice, water ice also melts, forming a subsurface ocean of liquid water. Charon, Pluto's largest moon, also experiences its own rebirth. Its water-ammonia mantle begins to thaw, creating lakes and even small seas of liquid water mixed with ammonia on its surface, a natural antifreeze that allows water to remain liquid at very low temperatures. For several 100 million years, Pluto, Eris, Makemake, and other objects in the Kuiper belt could become the most favourable places for life in the entire solar system. It is a striking paradox. Death at the centre of the system grants a short, fleeting life on its cold outskirts. If some primitive organic chemistry, or even the simplest life forms, were dormant in the depths of these icy worlds, under kilometres thick shells of frozen gases, they now have a unique chance. Warm water, organic compounds, stable conditions for hundreds of millions of years, all the necessary ingredients for the emergence and development of life. Perhaps new ecosystems are emerging in these distant oceans. Simple microorganisms feeding on the chemical energy of reactions between water and rocks. More complex forms utilising the organic compounds accumulated over billions of years of these worlds' cosmic history. But the most dramatic changes are happening to the moons of the gas giants. Europa, Ganymede, Callisto, the icy moons of Jupiter, receive enough energy from the red giant for their kilometre-thick ice shells to completely melt. Beneath them, the deepest oceans of liquid water are revealed, oceans that, by volume, far exceed all of Earth's seas combined. Europa becomes a true water world. Its ocean, once hidden under a 15-kilometre layer of ice, is now open to space. A dense atmosphere of water vapour forms above it. Perhaps even clouds appear and rain falls, the first in the history of this small world. Enceladus, the tiny moon of Saturn, also finds a new life. Its geysers, which for billions of years spewed jets of water vapour through cracks in its icy crust, now turn into real rivers and lakes. The moon's surface becomes covered with a network of reservoirs connected by channels. Even Titan, Saturn's largest moon, changes dramatically. Its dense nitrogen-methane atmosphere heats up so much that its methane lakes and seas turn to vapour. But at the same time, the water ice beneath the surface melts, and for the first time in its history, Titan acquires oceans of liquid water. This amazing time could last from 300 to 500 million years, a period long enough for life to emerge and evolve in these new oceans. Considering that on Earth, the first complex multicellular organisms appeared in a similar time frame, life in these distant worlds has a real chance. Imagine this amazing period in the history of the solar system. At the centre burns an unstable red giant, swallowing planets one by one. And on the periphery of the system, life flourishes. Europa's oceans teem with microorganisms. Complex ecosystems develop in the depths of Enceladus. The first multicellular creatures emerge on Titan. But this is only a temporary respite, a brief interlude in the grand cosmic symphony. The red giant continues its evolution, preparing for its final act, shedding its outer layers and transforming into a white dwarf. And when that happens, the short period of warmth and life on the outskirts of the system will also come to an end. The Planetary Nebula, the beautiful death of a star. 10 billion years in the future, the red giant phase is coming to an end. In the core of the Sun, which has been contracting and heating under its own weight all this time, the final thermonuclear reactions begin. Now helium, the product of billions of years of hydrogen burning, begins to fuse into carbon and oxygen. This process is even more violent and unstable than the previous stages of stellar evolution. The core temperature reaches 150 million degrees. The thermonuclear burning of helium occurs explosively, in pulses. The star enters its final agony. The Sun begins to pulsate with a period of several thousand years, contracting and expanding like a giant cosmic heart. But these heartbeats become weaker and more irregular. With each pulse, the star sheds its outer layers into the surrounding space at speeds of tens of kilometres per second. The gaseous shells that were once part of the star fly off in all directions, forming an expanding spherical cloud around the dying Sun. These ejections contain all the elements that were synthesized in the star's core over its billions of years of life. Carbon, oxygen, neon, magnesium, silicon, iron. And then comes the climax. All that remains of the giant star is its exposed, incredibly hot core, about the size of Earth, but with half of the Sun's original mass. This object is called a white dwarf. Its temperature reaches 100,000 degrees Celsius, 17 times hotter than the surface of the current Sun. With its powerful ultraviolet radiation, this scorching core illuminates the gaseous shells it has just shed. And one of the most beautiful phenomena in the universe occurs. A planetary nebula is born. The gas begins to glow brightly, shimmering with all the colours of the rainbow. Hydrogen glows with a characteristic red colour. Oxygen provides green and blue hues, helium yellow, and neon orange. Carbon and nitrogen add purple and magenta tones. Each element has its own unique spectral signature. Despite its name, a planetary nebula has nothing to do with planets. The name arose historically. The first astronomers observing these objects in 18th century telescopes thought they resembled the disks of distant planets. In reality, they are magnificent monuments to dead stars. The shape of the nebula depends on many factors: the star's rotation speed, the presence of a companion, and inhomogeneities in the ejected material. Some nebulae do resemble giant cosmic eyes, like the famous Helix Nebula. Others look like butterflies with colourful wings, like the Hourglass Nebula. Still others take the form of rings, spirals, or bizarre flowers. The nebula formed from the remains of our Sun will most likely have a fairly regular spherical shape. After all, our star rotates relatively slowly and has no close companion that could distort the symmetry of the ejection. The diameter of this nebula will gradually increase at a speed of 20 to 30 kilometers per second. 10,000 years after its formation, it will reach a size of several light years. That is greater than the distance from the Sun to the nearest star. The nebula's brightness will be truly fantastic. In the first few millennia after its formation, it will be visible to the naked eye from distances of thousands of light years. Observers in distant star systems will be able to admire this cosmic firework display, unaware that they are seeing the tomb of an entire planetary system. But this beauty is short-lived. It lasts for only about 10,000 years, a mere instant by cosmic standards. During this time, the nebula will expand and gradually dissipate into interstellar space. Its brightness will fade, the gas will become more and more rarefied, until it merges with the general background of the interstellar medium. The material of the nebula, enriched with heavy elements synthesized in the core of the dead star, will mix with interstellar gas and dust. Someday, perhaps hundreds of millions of years from now, gravity will gather this material into new gas clouds. From them, new stars and new planetary systems will be born. Carbon, oxygen, and other elements that were once part of our Sun will become the building blocks for new worlds. The cycle of stellar life and death will come full circle. Our Sun will have made its contribution to the great process of cosmic evolution, enriching the universe with the elements necessary for the formation of planets, and perhaps new forms of life. And at the centre of the slowly fading nebula, a small hot white dwarf will remain, all that is left of our once majestic star. It will continue to shine for trillions more years, slowly cooling in the cold emptiness of space. The Great Solitude, the epoch of the white dwarf. The planetary nebula has dissipated. The colourful cosmic show is over. 50,000 years have passed since its formation, and of the once brightest object in this part of the galaxy, only faint, barely discernible filaments of gas remain, dissolving into the interstellar medium. What is left of our solar system? At the centre, where our star shone for billions of years, there is now a small, dim object the size of Earth, but unimaginably denser. This is a white dwarf, the remnant of the Sun. A teaspoon of its material would weigh as much as a car. The surface temperature of this stellar corpse is still tens of thousands of degrees, but it no longer produces energy through thermonuclear reactions. It is simply cooling down, like a red-hot piece of metal taken out of a furnace. This cooling process will last an unimaginably long time, first billions, then trillions of years. The light emitted by the white dwarf has a harsh, bluish-white hue. It is much hotter and brighter per unit area than our Sun was on the main sequence, but its tiny size means that the total amount of energy radiated is relatively small. Around this stellar remnant at vast distances orbit the surviving planets. There may be 4, 5, or 6 of them. The exact number depends on how many worlds managed to survive the catastrophic events of the last few billion years. Jupiter and Saturn definitely survived. Uranus and Neptune most likely did as well. Perhaps Mars also survived, if it was lucky enough to avoid being engulfed by the red giant. Their orbits are now almost twice as wide as they were during the Sun's main sequence era. Jupiter's orbit has expanded from 5 to 9 astronomical units. Saturn has moved from 10 to 18. Neptune's orbit, the most distant of the survivors, has grown from 30 to 55 astronomical units from the centre of the system. The planetary system has become enormous, dark, and almost empty. The distances between the planets have increased so much that even in the most powerful telescopes, they would appear as nothing more than faint points of light, barely distinguishable against the starry background. Only a ghostly faint light from the cooling white dwarf falls upon these planets. In brightness, it is comparable to the light of a full moon in our time. This radiation is catastrophically insufficient to sustain any processes on the planet's surfaces. Eternal twilight and a cold close to absolute zero reign. Jupiter and Saturn, deprived of an external heat source, have completely frozen. Their turbulent atmospheres, which raged for billions of years under the influence of solar energy, are now calm and still. The upper layers of their gaseous envelopes have turned to ice. Jupiter's great red spot, a giant hurricane that had raged for centuries, has finally subsided. The moons of these planets have also plunged into eternal permafrost. Europa, which was a water world during the red giant era, is once again covered with a thick shell of ice. But now this ice is much thicker and colder than it was originally. The subsurface ocean, if it still exists, is tens of kilometers deep and is sustained only by the heat of radioactive decay in the moon's core. Titan has become a lifeless, icy desert. Its dense atmosphere has partially condensed and fallen to the surface as snow. The methane lakes and rivers that once adorned its surface are now permanently frozen. This is the epoch of the Great Solitude. The system is dead and motionless. The only processes still occurring are the slow orbital evolution of the planets under the influence of tidal forces and gravitational perturbations from passing stars. Time in this dead system flows very differently than it did during the era of the active sun. Changes happen so slowly that they are difficult to notice even over millions of years. The planet's orbits remain stable. Days and years follow each other with the same regularity as billions of years ago, but there is no longer any difference between them. The same cold and darkness prevail everywhere. It seems that this will continue forever, but even eternity, on a cosmic scale, has its limits. 10 trillion years after its formation, the white dwarf will have cooled so much that it will no longer emit visible light. Its temperature will drop below 4,000 degrees. It will become a black dwarf, a cold, dead ball of crystallized carbon and oxygen, invisible against the blackness of space. But even this is not the end of the story. Even more dramatic events await the system, which will finally destroy the last remnants of the once thriving planetary family. The final disassembly, the end of the system. 30 trillion years have passed since the Sun's death as an active star. A solitary, invisible black dwarf drifts through space, accompanied by 4 or 5 frozen giant planets. Their slow, majestic dance has lasted for an unimaginably long time in near total silence and darkness. The orbits have remained stable all this time due to a delicate gravitational equilibrium among the planets. But now, this multi-trillion-year dance is coming to an end. Our galaxy, the Milky Way, is a bustling and dynamic place. 200 billion stars are constantly moving in complex orbits around the galactic centre. They approach each other, move apart, and sometimes pass very close. And sooner or later, according to the laws of statistics, another star must pass near the remains of our solar system. This star might pass at a distance of hundreds of thousands of astronomical units, thousands of times farther than the current size of the system. But even such a distant passage will be enough to disrupt the fragile gravitational balance that has been maintained for tens of trillions of years. The gravitational perturbation from the passing star, like a stone thrown into a quiet pond, sends ripples through the planetary system. At first, these disturbances are almost imperceptible. The planet's orbits change by only fractions of a percent. But in a system of several massive bodies, even the slightest changes can trigger a chain reaction of unpredictable consequences. A slow but irreversible chaos begins. Jupiter and Saturn, the two most massive objects in the system after the central black dwarf, enter a gravitational resonance. their mutual attraction begins to destabilize each other's orbits and affect the motion of the other planets. First, the most distant and massive planet separates from the system, most likely Neptune. A series of gravitational interactions with Uranus and Saturn ejects it from the system. It becomes a rogue planet, doomed to an eternal solitary journey through the vastness of the galaxy at a speed of several kilometers per second. The loss of Neptune destabilizes the system even further. Now it is Uranus's turn. Gravitational interactions with the remaining giant planets gradually stretch its orbit into a long ellipse. At some point it comes too close to Saturn, receives a gravitational kick, and also leaves the system forever. This process stretches over billions of years. Each planetary encounter, each gravitational interaction, occurs in slow motion. But the outcome is predetermined. The system is inexorably falling apart like a house of cards. Eventually only Jupiter and Saturn remain, orbiting the black dwarf in highly elongated orbits. But their partnership cannot last forever. A chance encounter caused by another gravitational perturbation from a passing star results in one of the giants gaining enough energy to leave the system. Which planet will survive last? This depends on many random factors and is impossible to predict. It might be Jupiter, the most massive planet most tightly bound to the central body, or it could be Saturn. Its more distant orbit makes it less susceptible to tidal effects. The last planet might hold on for several tens of trillions more years, slowly spiraling towards the black dwarf due to gravitational wave radiation, a tiny effect predicted by Einstein's general theory of relativity. But its fate is also sealed. Sooner or later, it too will either leave the system or be torn apart by tidal forces. The process of the planetary system's destruction will take from 10 to 100 trillion years. It will be a slow agony, stretched over a period thousands of times longer than the current age of the universe, the final dissolution of an ancient stellar family. By the end of this period, all that will remain of the once majestic solar system is a solitary black dwarf, flying through the void of interstellar space. All the planets, all the asteroids, all the comets, all the dust, everything will have been either swallowed or ejected into galactic space. The system will cease to exist as a single entity. Epilogue. Traces of a vanished world. 100 trillion years in the future. The universe has become a completely different place. Most stars have already gone out or are in the final stages of their evolution. Galaxies are flying apart from each other at an accelerating rate. Cosmic space has become colder, darker, and emptier. Somewhere in this vast emptiness drifts a tiny invisible object, a black dwarf, the remnant of our sun. Nothing remains of the once rich and diverse planetary system. All the planets left their parent star long ago, and now roam interstellar space as rogue planets, or were torn apart by tidal forces. But will any trace remain? Any reminder that this was once home to billions of life forms, that there was a blue planet covered with oceans, where forests rustled and birds sang, that intelligent beings lived here, who dreamed of the stars and tried to understand their place in the universe? Perhaps, yes. When astronomers of the unimaginably distant future, belonging to civilizations whose nature we cannot even imagine, study the spectrum of this cooling black dwarf, they might notice faint, barely perceptible absorption lines. Spectral lines of metals, iron, magnesium, silicon, calcium. These elements should not be in the atmosphere of a white or black dwarf. They are heavier than the hydrogen and helium that mainly compose such stars, and should have long since settled into the core under the force of strong gravity. Their presence in the spectrum can mean only one thing. These atoms entered the star's atmosphere relatively recently, on a cosmic scale. And then, these astronomers of the distant future will understand. They are looking at the remnant of a star that once devoured its planets. The lines of iron and silicon are all that is left of the rocky worlds that orbited this star for billions of years. It is the chemical echo of long-vanished planets, the last trace of their existence. One astrophysicist poetically called these spectral lines the drops of blood from a long-dead planet. This is all that will remain of Earth in the distant future. Not the Great Pyramids, not Beethoven's symphonies, not the poetry of Shakespeare, not the scientific discoveries of Newton and Einstein. Only a few faint lines in the spectrum of a dying star, a chemical fingerprint in ancient light. But even these lines will fade with time. The atmosphere of the black dwarf will continue to cool and mix. The heavy elements will gradually settle into the star's core, where no one will ever be able to detect them. In trillions of years, even the last trace of our world's existence will disappear, and the universe will continue its evolution. Black dwarfs will cool in absolute darkness for trillions upon trillions of years. Protons, which make up all ordinary matter, may begin to decay. Even black holes, those last bastions of gravity, will eventually evaporate due to Hawking radiation. But that is another story entirely, one that goes far beyond the fate of our solar system. A story of how the universe will reach its final state. Cold, dark, empty, where only the occasional quantum fluctuations flicker in a sea of virtual particles. Our journey into the future has come to an end. We have traced the path of our cosmic home from its dawn to its deepest sunset. We have seen how stars and planets die, how nebulae are born, and how planetary systems fall apart. This story may seem bleak and hopeless, but it has its own special beauty, its own majesty. It reminds us how precious our moment in the sun is, how wonderful and beautiful our blue world is, full of life, here and now. We live in the golden age of the universe, when stars still burn brightly, when planets can still support life, when oceans and atmospheres, forests and civilizations are possible. This period will not last forever, but it is happening now, and we are part of this grand cosmic spectacle. The universe will exist after us. New stars will be born from the remnants of old ones. New planets will form around them. The carbon and oxygen synthesized in the core of our sun will become the building blocks for new worlds. And perhaps, on one of these planets, life will emerge again, and new intelligent beings will one day look up at their night sky, asking the same eternal questions that we do. What is time? What is space? Is there meaning in existence? Are we alone in the universe? But for now, we are here. Our sun is shining. Our earth is alive and beautiful. And we still have time, billions of years, to explore the universe, to understand its laws, to find our place in cosmic history. A time to dream, a time to love, a time to create beauty and seek truth, a time to be human on a small blue planet near an ordinary yellow star in one of the countless galaxies of the vast universe. Listen to your breath, feel your heartbeat. Our world is alive. Our sun gives us light and warmth. And in this lies a true miracle, the miracle of existence, the miracle of consciousness, the miracle that the universe, through us, comes to know itself.